This lecture will cover Big Idea 2, Standard 1. Today we're talking about orbital filling diagrams. So this is going to go hand in hand with our last lecture on Intro to Electron Configuration. So orbital filling diagrams are just one way to visually show an electron configuration. There are 3 rules that you need to know. So up first is the Aufbau principle. The Aufbau principle states that electrons must fill lower energy orbitals first. So this is just like when you're drawing a Bohr diagram. You would put 2 electrons in that first energy level before you would go to the second energy level. You would fill the second energy level with 8 electrons before going on to the third. The lower energy orbitals are closer to the nucleus, so we must fill those lower energy orbitals first. 2. Hund's rule. Hund's rule is what I like to refer to as the seats on the bus. Hund's rule states all orbitals must be filled with 1 electron before electrons can pair. So we learned last lesson that each orbital could hold 2 electrons, but we are not going to pair up 2 electrons in a single orbital until every orbital is filled. So imagine we have a bus. We would put like 1 student in each seat before we would go back and pair them up. Especially now with COVID, we want to socially distance. If we go back to school and you guys are taking the bus to school, there'll only be 1 student per seat. The electrons are the same way. We only want 1 electron per orbital. Once they're all filled, then we would go back and pair them up. The 3rd rule is called the Pauli exclusion principle. And in summary, what the Pauli exclusion principle is, it states that only 2 electrons can go in an orbital, which we know each orbital could hold 2 electrons, and they must spin in opposite directions. So if 1 electron is spinning clockwise, the other would go counterclockwise. So we said orbital filling diagrams are a way to show electron configuration. How are we going to show which way an electron is spinning? Well, we are going to show it with an arrow. So if your first electron is spinning clockwise, it's going to have an up arrow. And then the second one, if it's spinning counterclockwise, it's going to have a down arrow. Just to go over the symbols that we're going to use, since we said this is a visual way to depict our electron configuration. Anytime you see either like a box or a line, you can use either. That is going to represent the orbital. We are going to use arrows to represent electrons. And then we talked about this with the Pauli exclusion principle. The direction of the arrow represents its spin. So let's look at a few examples. For these first three, we are going to circle and explain the error. Okay, so let's say A looked like this. First, let's talk about the number of lines. Remember, in the last lesson, we said that there can only be one orbital for the S. There's only one S orbital. The line represents the orbital. Since there can only be one S orbital, I only have one line for S's. We said there are 3 P orbitals, so that's why P has 3 lines. The line, or if these were in a box, that would represent the orbital. So I have some electrons, and again, the way the arrow is pointing represents the way that they are spinning. So this one has a mistake. So take a second and see if you can figure it out. My mistake is right here in the 2s orbital. This is violating the Aufbau principle. We have to go in order. We're writing this in order of lowest to highest energy. Energy increases as we go to the right. So the 2s orbital must be filled before going on to 2p. You have to fill the lower energy orbitals first. We have to fill 2s before we can go back and fill 2p. B. So looking at this one, 1s looks good. An s orbital could hold 2 electrons, 1s is filled. I go on to the 2s. The 2s orbital is filled with 2 electrons, that looks good. Pauli's exclusion principle is good. I have 2 electrons in an orbital and they're spinning in opposite directions. Aufbau is good. 1s is filled before 2s. 2s is filled before 2p. So where's the mistake for this one? Well, it has to be in 2p, and this is where we're going to find that mistake. So again, pretend these are seats on the bus. I have 1, 2, 3 empty seats, and I have 2 electrons. Well, I need to put 1 electron in each of those orbitals. Once all of them have 1 electron, then I could go back and pair. So this would be what the correct 2p would look like. Rather than having 2 electrons paired up, I would have 1 electron in the first orbital and 1 electron in the second orbital. Remember, electrons are negative and like charges repel. These 2 electrons would repel. So rather than having them in the same orbital, they prefer to be in separate orbitals. So we need to explain the error. Each orbital must be filled with 1 electron before they can pair. Let's do one more for finding the mistake, and then I'll have you guys do some that are correct. looking at this one, off-BA principle looks good. 1s is filled. Then we go on to 2s. The 2s is filled. Once the 2s is filled, I then put electrons in the 2p. That looks correct. Hund's rule looks good. 1 electron in each orbital before they can go back and pair. So hopefully we saw the mistake is in that 1s orbital. This is going to violate Pauli's exclusion. Pauli's exclusion principle. Electrons in the same orbital must spin in opposite directions. One thing to keep in mind when you are doing these explanations is make sure you're using proper terminology. Don't say 2 arrows on the same line are pointing up. That's not going to get you credit. Arrows represent electrons, so 2 electrons. The line represents the orbital, 2 electrons in the same orbital. Rather than saying they point up, the direction represents the spin. So 2 electrons in the same orbital cannot spin in the same direction. So just keep that in mind. Try not to use pointing up, pointing down, arrows, box, or line. We don't want to use any of that terminology. What we want to use is orbital, electrons, spin. All right, let's draw some that are correct. Draw an orbital filling diagram for, let's do carbon, sodium, and let's do an ion. So first thing that we need to do is we need to head to our periodic table and we need to know how many electrons we need to draw. So for the first one, I don't see a charge, so we're going to assume that carbon is an atom and atoms are neutral. Carbon has an atomic number of 6. That means it has 6 protons. It also has 6 electrons. We are going to fill the lowest energy orbital first, which is 1s. An s orbital could hold 2 electrons. They must be spinning in the opposite direction. Once the 1s is filled, we're going to go on to the 2s. Again, an s orbital could hold 2 electrons spinning in opposite directions. So far I've placed 1, 2, 3, 4 electrons. I have 2 more to go. Once I get into the 2p, remember Hund's rule, seats on the bus, fill every empty orbital with an electron before they pair up. P could hold up to 6 electrons, but remember we only need 6 total. 1, 2, 3, 4, 5, 6. We could then convert this right to an electron configuration. Remember, arrows represent electrons. Carbon's electron configuration would be 1s2 because I have 2 electrons. 2s2, 2p2. So this is the same thing that we started yesterday. The only difference is we are representing it with some symbols. Sodium, Na. Atomic number 11, 11 protons, 11 electrons. Again, we're going to fill the 1s. We can then fill the 2s. S orbitals hold 2 electrons. Hund's rule, seats on the bus. We are going to fill every empty orbital into P. Once they're filled, then we can go back and pair up. So far we've drawn 2, 4, 6, 8, 10 electrons. I need one more. So 1 in the 3s. Sodium and carbon were both atoms, but we would do this the same way if I had an ion. Nitrogen, atomic number 7. So nitrogen has 7 protons. That means I have 7 positive charges. Nitrogen has a charge of -3. So how many electrons would I have? Well, if my overall charge is negative and it's a -3, I have to have 3 more electrons than protons. So that means I would have 10 electrons to place. We should remember this from the first unit. So again, we're going to fill the 1s orbital with 2 electrons. They must be spinning in opposite directions. Once the 1s is filled, we're going to go on to the 2s. Again, we can fill an s orbital with 2 electrons spinning in opposite directions. When we get to the p orbital, we are going to fill every empty orbital with an electron. Once they're filled, then we can go back and pair. So far I've placed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So drawing an electron configuration or an orbital filling diagram for an ion is exactly the same as an atom. The only thing that is different is you need to calculate the correct number of electrons to draw.